All right, we'll give folks a minute to get situated. Wow, I wish that worked in class. Well, with silence like that, okay. So welcome to APS Colloquium today. Today, we're very fortunate to have our own Zach Berta-Thompson. Professor Berta-Thompson got his PhD at Harvard working with Dave Charbonneau. Then he moved to MIT as a Torres Fellow before coming to CU as a professor in 2016. So since Zach has been here, he's done all sorts of amazing things, is a regular and lauded guest observer with Hubble and James Webb, has also served on the executive committee for the Early Release Science program for JWST's Exoplanet program, serves on the the Telescope Advisory Council for Roman, and on and on and on. I want to also really emphasize all the work that Zach has done. He's probably one of our best teachers in our department, and has done thank you. And has done tremendous work on the climate and culture here in APS. So I give my 1 minute that I'm going to take from Zach's time. So I get to teach astronomy 3520 a lot, and during the AST 3520 field trip, we drive the students down and back in these 15-passenger vans, and I don't get airline miles for it, so I don't know what I'm doing with my time. But so I always have these 12-hour drives to talk to our seniors, and I always ask the seniors what was the best class you took in APS, and then I also ask them what the worst class was, but we won't talk about that. And over the last couple of years that I've been teaching this class, far and away the students say any class that Zach taught was the best class I took in APS. So it's really excited to have him tell us about small planets around small stars, and let's give a nice round of applause to Professor Berta-Thompson.
Thank you, Kevin. Thanks, Kevin. All right, and thanks all of you. Thank you for being here. So today I'm sort of gonna tear up all of the work that I've done since grad school till now. But don't worry, I think it's gonna be okay. So first of all, I just want to say happy Northern Autumnal Equinox, everybody. This is the special day of the year where your local time is the right ascension that is passing over zenith at this exact moment. So tonight, if you go out at 8 p.m. or I guess 9 p.m. with daylight savings, the Kepler field is overhead. So that's where most of the transiting planets that we know of in the sky. Go out, look up, see the Kepler field. Okay, so today I'm going to talk about a few different science projects. All these results kind of build on a lot of important places. So for me, that's my family, my wonderful research group, the entire department here, many of you in this room, the faculty and the staff and the students here who've been so supportive over the years, and of course the global astronomy community that we're all a part of. And I also have to thank the US taxpayers for funding through the NSF and NASA and the Space Telescope Science Institute, and CU tuition payers as well. Thank you very much for paying my salary for many months of the year. And then of course also the facilities and grounds and maintenance folks who built our buildings and keep us clean, and then the people who've been observing from these lands for hundreds or thousands of years before us. So the Cheyenne, the Ute, the Arapaho, and other indigenous folks. So today, I'm not going to talk about a lot of things. I'm not going to talk about many of my previous PhD students' work. I won't talk much about work we did with Hannah Diamond Low doing ground-based transmission spectroscopy observations, sort of initial steps in trying to find atmospheres around rocky planets. I won't talk much about Jessica Libby Roberts doing Hubble Space Telescope transmission spectroscopy of low-density planets and rocky planets. I won't talk much about Girish Devuri coming up with, I think, one of the best kind of standard ways of estimating the extreme UV emission from stars that's still being used widely in the field today. And I won't talk that much about work that we did with Will Wachs doing planet discovery and stellar characterization. I'm going to talk about mostly things from the past few years. So it's going to center on this question of which planets have atmospheres. We're in one right now, but we can cast out a little bit broader and we can ask this question more generally. And so of course, planets are always losing atmosphere. Even Mars today is losing atmosphere to space. So these are some simulations of Martian atmospheric escape plotted here by Muriel Cardana, who's simulating what this kind of escape might look like for transiting systems around other stars. But this question has a lot wrapped up inside of it, of which planets have atmospheres. So that's secretly asking, like, how efficiently does the stellar energy that hits a planet translate into escape from that planet, whether that be in the form of light or particles or magnetic fields, whatever it is, how much energy are we putting into atmospheres to drive them away? And there's also the question of, like, what do we start with for a planet? Like, what's the initial volatile budget for a planet? How much do you form with? How much do you accrete later on? And of course, those together, that's like, there's a timing here, right? You're losing things dramatically in your early days as a planet, but you're also gaining and outgassing and accreting. And so there's this timing of when do things balance out that you can actually let an atmosphere sustain and grow. And naturally, this builds into a question that certainly is interesting to me is what sorts of habitable environments might be out there beyond the solar system or within. And then, of course, just the big one, like, even if there are habitable environments there, is there anybody living there, whether that's intelligent people or microbes or whatever? We need to know that a planet has an atmosphere before we can start thinking about life existing there. So our goals for today, a little ambitious, but I think we'll get through it all. So I want us to leave here geeked to use transiting exoplanets as laboratories for understanding how planets work. I want you to be aware of some of the tools we're using with JWST to study the atmospheres of particularly rocky planets. And then I want to introduce you to a new probabilistic model for this question of which planets have atmosphere that we can apply in lots of situations. And then also just kind of generally to be excited about observing exoplanets, because I think it's a neat thing to do. And this is perhaps sort of a maybe more of a personal professional goal, ideally with tenure as well. So how do we study exoplanets? We build on our expertise as astronomers. Astronomers have spent 100 years getting really, really good at measuring the brightness of stars very, very, very precisely. These are the Harvard computers, women astronomers working at the Harvard College Observatory about a century ago. You might recognize Henrietta Swan-Leavitt up there, whose observations of pulsating stars, of course, taught us the distances to nearby galaxies and that the universe is expanding. And the methodology back then was photographic plates and pen marking each individual star on there, a fly spanker that's a little piece of glass that has some standard stars exposed onto it, and so you can compare how bright stars you see in a photographic plate are to what you see in this reference. And at that time, in the 1920s, precise photometry was like, really precise photometry was at the kind of percent or few percent level. It's incredible to think that you can do this, but they were making measurements at this level. And so now in the 2020s, I would say like really precise photometry measuring the brightness of the stars, to me that is like 10 to the minus 5, 10 parts per million. And that's primarily coming from JWST. So what this looks like is if we go and we measure the brightness of a star, I wanted a stick and I forgot a stick, and so this is not graceful, but it's going to work. We're just measuring the brightness of a star over time, and every time the planet passes in front of a star, you'll see a little dip in the brightness of the star. Here it's about 1%. In this case, that brightness dip is corresponding to the ratio of the planet's area to the star's area, just a circle blocking another circle in there. And so we can measure the size of a planet by measuring the brightness of that star over time. And we can do a lot more with that, bringing in complementary observations. We can measure the planet's size. We can also figure out the planet's orbit. We can measure the planet's mass. And in many cases, we can study a planet's atmosphere. So for transiting planets, those that happen to pass in front of their star, you can learn a lot. And so not all planets transit, but those that do are the ones that I like to study the most, just because they're the most fun. So I'll introduce you to our population of transiting exoplanets as we know it. And I'm going to take all of the beautiful data that we have on the 8 solar system planets and other objects floating around there and condense it down into just a few numbers so that I can compare it on the same footing as exoplanets. So on the left here, we have a planet mass and planet radius. And there's a curve here that is just sort of a generic model. If I took a ball of rock and iron of a particular mass, how big would it be? And that does a decent job of matching the 4 rocky planets in the solar system. Once you get above that, you need to have some sort of gaseous envelope to explain your radius. There's something that makes you a little bit puffier and less dense. So if we add the exoplanets onto here, you see that they follow approximately the same trend, right? You have this cluster of objects, the small planets really cluster along this rock-iron model. So small planets don't have thick hydrogen-helium envelopes. But then as you go to more massive planets, then you start having to have more and more gas to explain your radius overall. And you rise up to Uranus and Neptune, and then ultimately up to Jupiter and Saturn up there. OK, so I can add another axis on here. That this is planet bolometric flux received. This is how much energy do you receive from your star. I'll do astronomer axes with the big numbers on the left. And so 1 on here corresponds to the 1360 watts per meter squared that Earth receives from the sun. To the left is you're closer into your star, and so you receive more. To the right is that you're farther out from there. And so that can also correspond roughly to an estimate for an equilibrium temperature for your planet as well, either much hotter or much cooler. If we add the transiting exoplanets onto here, we see we have a lot of very hot transiting exoplanets. This is not because those are the only planets that exist. Those are the ones that are easy to see. It's easier to see a planet that is closer into its star. So there's a very strong selection bias for finding big things and finding things that are very close in. But this is a sample that we have to work with now, that we have planets stretching all the way from just above the surfaces of their stars out to Earth's orbit or even beyond. And we have objects that are the size of the terrestrial planets in our solar system as well. And so we can really start to compare to them. I'll add one more axis on here that is particularly boring for solar system planets. This is what is the size of the star that you transit. In the solar system, everything transits, well, it doesn't even necessarily transit. It orbits a 1 solar radius star. So everything's 1 on here. But if I add the size of the stellar host for all of the other transiting exoplanets, we have things that go down to 1/10 the size of the sun up to a few times the size of the sun. So what that corresponds to is not just, oh, the star is bigger or smaller. Different stars have very wildly different behaviors. And so in particular, we'll talk about today how much smaller stars have much larger sources of energy that could drive atmospheric escape and be sort of rough for the planets that orbit around them. Just looking at these with kind of basic observables for exoplanets, the big ones on here, they have atmospheres. If something is bigger than about 2-ish Earth radii, it basically has to have some sort of gas-rich envelope on there. Whether that is, at the low end, it could still be a pretty heavily enriched atmosphere that has a lot of water, carbon dioxide, whatever, ices stuff. But then as you go bigger, basically has to have hydrogen and helium in it. So for many planets, you can look at it, just know its mass and radius. Definitely know that has to have an atmosphere. For the smaller planets, they might have atmospheres. It doesn't contribute appreciably to its radius. And so you could look at an object based on its mass and radius and say that's a rocky planet. Maybe it's like Mercury or the Moon with just a tenuous exosphere, or maybe it's like Earth or Venus or Mars that has this richer atmosphere where lots of cool stuff is happening. So to figure that out, you have to actually go directly observe. And so how do we observe rocky planet atmospheres? There's one method that's super neat. The idea of exoplanet transmission spectroscopy. This is like measuring the light that travels over your shoulder at sunset, but from another planet. And this is the idea that because of absorption in Earth's atmosphere, our size as a planet varies as a function of wavelength. Because our atmosphere absorbs at some wavelengths, our planet is a little bit bigger at some wavelengths. And so if you measure the size of our planet very, very carefully, you could pick up molecular absorption in our atmosphere or scattering through the atmosphere and figure out the composition of what's in the atmosphere. And then for a sense of scale, if we look between 400 nanometers and 700 nanometers, that's the kind of bluest and reddest that we can see with our eyes. Earth is about 10 kilometers bigger in the blue. Our atmosphere is good at scattering blue light. So this is why the sunset looks red at sunset, is because there's this blue light is scattering away and making our planet effectively a little bit bigger as seen from far away. But then as you go farther into the infrared, you have lots of molecular absorption features that you could pick up. This is neat. This is super fun. I love these observations. They're terrifying and complicated because stars are terrifying and complicated. These are really complicated by the fact that stars are not just perfect uniform light bulbs. They have all these complicated surface features on them. So you have spots and plages, and all of this heterogeneous surface of a star means that you can't say, like, do this very simple geometry of like RP over R star squared and figure out the size of your planet. So for example, because star spots have a different spectrum than the rest of their star, if I put Earth in front of a typical small star and M dwarf, even if Earth had no atmosphere whatsoever, I might measure something that looks like the red curve, just because of the messy, complicated spectra of the star spots on that star. And so there are wiggles in both of these that would certainly be hard to disentangle. It would be particularly hard to disentangle things around here and here, where M dwarfs are cool enough that they have water in their atmospheres. We're often trying to look for water in exoplanet atmospheres. And so if you're seeing these same features appearing both in your star and your planet, it's going to be really, really hard to disentangle and figure out super confidently what's coming from the planet and what's coming from the star. And so I'll want to tell you about another observable that people are really we're using a lot these days, which is to watch when the planet passes behind its star. And so here, instead of that big giant transit that's happening, if you look really, really carefully, a half an orbit later, there's a little itty bitty tiny dip there. These data aren't binned, but maybe if you squint, you can just say, oh, there's a tiny dip. That's the tiny dip of the planet disappearing behind its star. These are observations at optical wavelengths where the planet isn't providing that much light to the system, but you can detect this tiny little dip when the planet disappears. And so by measuring that, you can learn about the flux that's emanating from the surface of the planet itself. You can measure its temperature. You can measure its thermal emission spectrum. So instead of you don't have to care about the surface of the star at all. You just need it to momentarily block your planet so that you can figure out what the flux was that came from that in the first place. So for a sense of like wavelength scale here, we're mostly used to the visible light from like 0.4 to 0.7 microns. If I look at myself with a thermal infrared camera of kind of 8 to 12-ish microns, using a camera that I borrowed from Nick Schneider, thanks, Nick, things look different, right? Because in the thermal infrared, you're seeing what's being emitted from my warm face, and then the places where I'm being insulated, you're not seeing as much light coming out because that's colder in terms of the light that's being emitted. Of course, many of you grad students have spent a lot of time with the Planck spectrum, and so you know that whatever temperature your surface is sets the wavelengths at which you'll be seeing the most light. So in this case, if we're talking about things of a few hundred Kelvin, we're only going to be seeing things way out in the thermal infrared. But if we talk about star temperatures of a few thousand Kelvin, then you can have visible light here. So transmission spectroscopy has mostly been done where the star is bright. For this emission spectroscopy, we want to look where the planet is bright. And so if you go and make a measurement outside near Earth's surface, you'll see two kinds of light, right? You'll see the incoming light, that is the shortwave radiation coming from the sun that reflects off of things, but some of that gets absorbed and heats up our surface, and then our warm surface emits that back out again. And so if you look in the infrared, you're mostly seeing just that thermal emission from our warm surface. And on a planet, that's set by a very particular energy balance, that whatever gets absorbed by a planet has to ultimately heat up the planet and radiate as infrared radiation. So here on the left, this snow is very reflective, so it doesn't absorb a lot of light. This asphalt is very absorbing. It absorbs a lot of light. The snow reflects a lot of light, is very cold. The asphalt absorbs a lot of light. It heats up and is therefore very warm and emits here. And so this balance happens globally for Earth as a planet, and it also happens on local scales for a planet. And so we can use that to learn about the surface of the planet or the atmosphere of a planet by measuring this thermal emission. With Hubble, we've mostly been restricted to the optical. With JWST, we finally have access to these infrared wavelengths where we can see the emission from planets themselves. So I want to tell you about one project where we used JWST to observe LTT 1445AB, everyone's favorite planet, I know. This is an object that you can tell that it's a rocky planet. Its mass and radius are consistent with a rock. It receives about the same flux as Mercury. So it's Mercury, but much bigger. but then it orbits around a very small star. And so that fact makes it particularly easy to observe. Because the star is so small, it contributes relatively less light to the system as a whole. So Pat Wachirapan worked very hard on these very complicated MIRI LRS observations with JWST and got us to this point, where our data on the left are a measurement of how bright is the system as a function of time on the x-axis and wavelength on the y-axis. You'll notice the wavelengths are these sort of 6 to 12 microns, the thermal infrared here. And then you'll hopefully notice in the middle here, there's this little dark band. That's the brief moment of an hour and a half when the planet is behind the star and not contributing its light to the system. If we fit this with a model here, we end up with residuals where the planet's emission disappears and all you have is the emission of the star itself. So these observations tell us this planet doesn't have an atmosphere. Anyone know why? It's complicated, I'll tell you. All right, so here's the cartoon version. So thermal emission can tell you whether or not your planet has an atmosphere just by looking at Earth and the moon. Again, Pat made these really beautiful plots digging into real solar system data of the Earth and the moon so that we can have a better reference for exoplanets. So Earth has an atmosphere and it rotates quickly. That means all of this energy we receive from the sun gets distributed really uniformly over our entire sphere. And so if you make a map of our temperature, it's pretty boring. The temperature doesn't drop to absolute zero at nighttime, which is great for us here on Earth. But what that means is that our day side is relatively cool because there's a lot of energy that gets redistributed over to the night side of the planet. So energy comes in, some of that goes around to the night side, some of that comes out on the day side, which is what we can actually observe from JWST when this planet is like right behind the star staring at us. The moon, on the other hand, has no atmosphere. Energy gets absorbed locally and then warms up that surface and then radiates locally away. And so if you make a temperature map of the moon, you'll see it's very hot at the substellar point at noon where the sun is straight overhead, and then it falls off smoothly towards the edges, and then it's very cold on the night side of the moon. So here, energy comes in, you have lots of emission right overhead, and then this falls out, and then there's none on the back of the planet. Yes, I have made some of you in this room calculate equilibrium temperatures for planets. And there's always this assumption that we do in our intro classes where we say, okay, we have this energy that's coming into the planet, that's our power in. And then our planet is emitting radiation according to some temperature. And the planet has all one temperature, and so it emits over an area of 4 pi r squared. And I can use this to calculate the equilibrium temperature by planet. Make sense to folks? There's always that one kid who says, like, but what if the planet doesn't emit the same everywhere? They're totally right. So for example, if you only emitted over half of your planet, this would switch from 4 pi r squared to 2 pi r squared. If you do this really carefully, with this whole kind of weighting more towards the substellar point, this works out to an effective area of 3/2 pi r squared. And so this gives you a much hotter temperature for your day side if you don't have an atmosphere. That is much hotter than that otherwise kind of average equilibrium temperature that you would calculate. And so these eclipse depths that Pat measured are consistent with this. They are so deep. I know they look noisy, but they are so deep that we can only explain them with a really hot day side for the planet. So here's what this looks like in terms of eclipse depth, the thing that we can measure as a function of wavelength. And on here, this curve kind of points towards an Earth-like scenario of uniform heat redistribution everywhere. This top curve points towards more of the moon-like scenario of planet instantly re-radiates the energy it receives. And our actual best measurement for a single temperature on here points a lot more towards that moon-like scenario. We have a temperature that is only about 25 Kelvin cooler than that maximum temperature for the planet. And so that by itself is evidence that there's not a really thick atmosphere on this planet, sort of Venus-like atmosphere that is redistributing heat around to the night side. And we can also look at this emission spectrum and compare it against a suite of models where, of course, atmospheres have absorption features as well, right? They have greenhouse effects. And so we also don't see the features that we would expect from a thick atmosphere on here. This is the closest thing we have is kind of isothermal. And it's not a perfect model, but it's the best we have. Yeah, no.
So on your conclusion that, okay, if it's much hotter, it must have an atmosphere. the other thing about the moon is it's much more slowly rotating than the Earth, right? It's once a month. So what's the dominant effect there? Is it the atmosphere, distributing the temperature around the back, or is it, not? Is it the lack of atmosphere not distributing around the back, or is it the fact that it's slowly rotating?
Yeah, so Nils was asking this question about how the competition between rotation and atmosphere in here. Is the rotation more effective for redistributing heat, or is atmosphere? In the case of I'll answer it the other way, that for Earth, if you had a 1-bar atmosphere, but Earth was rotating slowly, it was tidally locked, you would still have a pretty hot day side. 1 bar is enough that you can avoid atmospheric collapse on the night side, but it's not enough to really smoothly redistribute the energy around to the night side. Pat, did I say that correctly? He nodded. Great. But then in the case of the moon, if it were rotating much more rapidly, then yes, you could have something that is more uniform in temperature. That's a question I would probably put to Kaya, who's doing this for really short, rapidly rotating objects in the solar system.
So the hot day side, there's evidence for the hot day side that could indicate either lack of atmosphere or slowly rotating or both. Is that right?
So for most of these observations, the time scale for tidal synchronization is really short. And so our default assumption for all of these is these planets are tidally locked with a permanent day side and a permanent night side. We could use the fact that we see this hot day side to make some sort of statement that we are pretty close to tidally locked, in that if it were rotating more rapidly relative to this, then we wouldn't see this hot emission. So it's effectively infinitely slowly rotating in the frame of the star. Okay, so putting these pieces together, we have this evidence that points towards this planet, this super Mercury. If it has an atmosphere, it's probably less than 1 to 10 bar. And I know that there are people in this department who study atmospheres that are much more tenuous than that, and those are still great atmospheres. But for exoplanet standards, this is pretty gosh darn good that we can place a limit like this on the presence of an atmosphere for a rocky planet. And so the question now, of course, is does it lack this atmosphere because it is just too hot? Mercury and everything hotter than that will never have an atmosphere. Or is there something else going on? Because it's a pretty big planet, so it should be able to hang on to something. And so the other hypothesis is effectively that the star is too small. It's an M dwarf that's too active, that is too good at stripping planetary atmospheres. And so after this project, we really wanted to have a way to contextualize these observations that we and other groups are making to put them into one picture of how do we understand what we're seeing for atmospheres being there or not. And those other folks include the huge community who are involved with this JWST Rocky Worlds program. So this is a 500-hour DDT program to go gather 15-micron thermoinfrared photometry of rocky exoplanet eclipses to search for atmospheres using this method that I just described here. So to try to do a broad survey so that we don't have to do it all individually. And one of the organizing tools that they're using is that one of the best tools that we have, this idea called the cosmic shoreline. That is, if you make a plot of how able to hold on to an atmosphere is a planet, so escape velocity here, estimate of gravity, and then how much energy is impinging on that planet that could erode that atmosphere away. So here, this is relative cumulative UV irradiation. You can make different versions of this, but they're saying things that are down here are more likely to have atmospheres. There's a line that's drawn on there, and that line comes from this paper in 2017. The cosmic shoreline, there's lots of really cool planetary science in here, and lots of really neat ideas that are being tied together. And they say in here that this dividing line goes as v escape to the fourth. I'll show you their plots. This is one of the key figures from that paper. So escape velocity on the x-axis, I now in terms of bolometric installation on the y-axis, how much energy you're receiving from your sun. And then, the solid symbols are things that have atmospheres, the open symbols are things that don't, and the colors are distracting. But it's this neat idea that atmospheric loss is going to be some balance of energy and coming in, and this gravitational energy lift that you spend lifting an atmosphere off of a planet. And so you can kind of see that things line up along here. But of course, one of the first things that we teach about atmospheric escape is, and Jeff Linsky walked into the room exactly at the moment when I started talking about XUV radiation. Perfect timing, Jeff, thank you. So that escape happens from Earth's upper atmosphere. Earth's upper atmosphere is heated by X-ray and extreme ultraviolet radiation. So our surface is mostly heated by optical and infrared. Where escape is actually happening is heated by this very tiny fraction of the sun's spectrum that carries a lot of energy per photon. And so this is particularly troublesome when we want to start comparing the sun to exoplanets around other stars, because other stars emit different amounts of XUV radiation. So a plot from David Wilson here at LASP shows the relative spectra of the sun in yellow, a kind of early M dwarf in orange, and then a late M dwarf, a very small M dwarf in red. And you can see on here that these M dwarfs emit something like 100, 1,000, 10,000 times more energy, a larger fraction of their energy in the XUV compared to the optical. And so if that is the energy that's driving escape, we need to account for that in some way. And so this original Zonley and Kathleen paper incorporated this in terms of a y-axis for this plot that is relative cumulative XUV irradiation. So trying to put that on there, we have measurements of this we have measurements of the cumulative XUV irradiation that planets have experienced for exactly 0 planets, not even in the solar system. Because it's relative, we could give us the solar system, but we don't even know the sun's XUV history all the way back into the past, and we certainly don't know this for every other star that we're out here, that we're measuring out here. And so it matters a lot, but it's really, really hard to estimate. And so that's one frustrating problem with this. The other one is that the line that they draw on here that is now being used to guide the 500-hour JWST Rocky Worlds program was drawn by eye, which is like, cool, it's great that you could find a line on here, but like, let's measure this. Gosh darn it, we can do it. We're scientists. And so we set out to do this project where we tried to measure the location and the slope of this cosmic shoreline. And we've also introduced a kind of fuzziness into here, right? Because we know this isn't just going to be one exact line. There's going to be some range where there's a probability that you do or don't have an atmosphere. And then along the way, we're also going to try to avoid estimating these XUV histories for individual stars. We still have to account for the fact that M dwarfs will, on average, be emitting more XUV radiation, but we're not going to have to say, I know the exact history of that individual star. So I want to walk you through this equation because the model is like pretty simple, and I think it's useful, and there's some kind of fun physics that we can learn from it, even though it's entirely empirical. So we define a shoreline flux in terms of the bolometric flux that a planet receives from its star as just some constant times a v escape to the p times the stellar luminosity to the q. And so this is adding in some dependence on stellar luminosity in here, where q, p, and f are going to be free parameters in my model. And then escape velocity, ooh, that color does not show up at all. Escape velocity and the L star are things that we can actually measure. And so you can kind of think of the first half of this equation as how does the incoming stellar energy lift atmospheres off of planets? And also a little bit what was their initial volatile budget. And then you can think of the second half of this equation as how do those drivers change as you go to different types of stars? And in here, I'm making a very big assumption that this is just one power law in both dimensions, but we have to start somewhere. And we start there because this is a really nice, simple model. If you take the log of this looks like just a plane, right? There's like some constant, a slope times a thing plus a slope times another thing. It's just a line in 2 dimensions. And so we can define a probability that any planet has an atmosphere using this shoreline flux based on the distance of the flux of any particular planet relative to the shoreline flux that is defined for it. And so if you're over here that you have like, you're receiving way less flux than your shoreline flux, you're a cool planet and you probably have an atmosphere. If you are way over here that you're receiving way more flux than your critical value, then you have probably lost your atmosphere. And so just a smooth curve on there. So we define that probability. we take the whole sample of solar system planets and exoplanets, and we label them binary, do you have an atmosphere or not? There's a lot of fuzziness in there that I won't talk about at all. But these are the data that we fit to. So escape velocity, flux received, and then I have panels here for different stars. So this is like solar luminosity stars, 1/10 the sun's luminosity, 1/100th, and 1/1000th. So our smaller stars are over to the right on here. And the brown points don't have atmospheres, the blue points do. In the solar system, this is pretty easy. For exoplanets, really the only planets for which I'm saying we don't have an atmosphere are ones for which JWST has made the kind of observation that Pat and I made for the LTT 1445, where we see a hot day side coming from it. That is our, we don't have an atmosphere. Everything else we're agnostic about. So we take these data, we use NumPyro to do an MCMC to figure out these 4 parameters, our the shape of the shoreline and this intrinsic width, the fuzziness of our transition there. And just to say, if you haven't been using JAX and NumPyro for your MCMCs, it is magical. There's, so in here, there are 4 parameters that we wanted to fit. And then we also had about 1,000 planets, and each of those 1,000 planets had uncertainties in 3 dimensions. And so we just included 3,000 additional parameters to account for the true values of those planets and marginalized over all of those as nuisance parameters to get to the 4 planets that we wanted. And it took about 5 minutes. It's amazing. So MCMCs are really fun these days, just in case you're missing out. But here's what we get. This is our best fit shoreline in here. Where the brown is the sandy no atmosphere and the blue on here is you can have an atmosphere. And you can see it does a pretty good job matching the solar system planets, and we'll try to zoom in on those other ones as well and convince you it does a decent job there as well. For scale, this is kind of sun-like stars here, G2. This is late Ks, early Ms, late Ms, all the way down there. I have to, it's tricky because this is in this 3D space, and so we need some way to represent that. And so I'll just animate this now by kind of slicing in luminosity. So we're looking at sun-like luminosities, and then, and then we will scan down to the very faintest stars and then back up again. And as you look at this, you'll see in most cases we're doing a pretty good job of the things that we label as not having atmospheres are on one side of this boundary, and the things with atmospheres are on the other. And I've on here, we're trying to connect Pluto has ices on its surface to the very hottest exoplanets do or don't have atmospheres. You might say that's not a thing we should try to do. Let's zoom in on a more reasonable region. And so if we zoom in on and say we only care about CO2 atmospheres, let's say a temperate terrestrial planet is probably going to have a CO2 atmosphere unless there's water to suck it down into limestone. Then if we zoom in on a region where only CO2 would be in the gaseous form, we still get a pretty good fit to this, that everything still lines up pretty well in here. And we end up with a similar slope and a similar width on here as well. And so remarkably, you can kind of step back and take this broad view of does a planet have volatiles or atmosphere, and it gives a pretty good approximation for even this range. So what that looks like in terms of parameter posteriors here for these 4 parameters that I care about, here, if I know many of you have looked at corner plots, but for those of you who have not, the top here is showing just histograms of the parameters that I'm inferring, and then the off diagonals are showing contours saying I'm 68 or 95% confident that the parameter is within this range in this particular parameter pair. And so if I look at any atmosphere whatsoever or just these warm CO2 atmospheres, I'll flip back and forth between these. And we get larger uncertainties if we look at this smaller region, but otherwise things are pretty consistent. So I'm going to proceed with my overall shoreline, and you can come back and ask me about the differences with that CO2 one later. But I do want to tell you about each of these parameters, because I think they're all pretty useful. So this normalization constant here of log f is about 2.7. That means that if I take an Earth-like planet around a sun-like star, I could move it in so that it receives a flux that is about 600 times the flux that Earth receives from the sun right now. That's like 0.04 AU. And that's where your shoreline is, and you would lose your atmosphere. That was sort of surprising to me, that that's like pretty close to the sun to be able to hang on to an atmosphere. Obviously, it's a very different atmosphere at that point, but this is, that's what this linear extrapolation would predict. If I look at the slope, this P, how strongly do we depend on the escape velocity, this balance between incoming energy and ability to hang on to things, we find here that an increase of 10x in escape velocity for the strength of gravity in your planet will permit atmospheres up to 1,000,000 times higher flux that you're receiving. It's a very, very strong dependence on your surface gravity for retaining an atmosphere. And just to say it, it's not 4, as it turned out. So this, like, the Zonley and Kathleen estimate that this value is going to be 4, that's not what we measure when we measured it. We find something that is consistent with, well, it's a few sigma away. If you look at the solar system itself, that works, but if you put exoplanets into there, they don't. This value does kind of fall between reasonable limits for, like, genes escape or energy limited escape, and so I think the number makes sense, and there's something interesting we can learn from exactly that slope, and this is something I'd love to, like, for us to be able to try to simulate from a first principles perspective. But for now, we can use it as just an empirical description of the planets we see. And then this Q parameter, this, like, dependence on the stellar luminosity. So this tells us that a decrease of 10 in stellar luminosity moves our shoreline down by about a factor of 20 in terms of flux. So your star gets 10 times fainter, but you need to be so far away that you're receiving 20 times less flux from that star. That's a, like, sort of scary number. So I want to, like, put that in context visually. This is a plot of, like, why exoplanet people love M dwarfs. This is like the habitable zone is closer to small stars. It's great. This makes them easier to observe because you only have to watch for 2 weeks to see a habitable planet instead of waiting for an entire 365 days. And so in terms of stellar luminosity on the y-axis, semi-major axis on the x-axis here, the TRAPPIST-1 planets down here are, like, our easiest habitable zone planets to study because they are around such a small star and orbit so quickly. So if this parameter Q, the dependence on stellar luminosity, were 0, then that would mean our shoreline just tracks with that habitable zone. It's parallel to it. There's some threshold, but hopefully it's interior to that, and we don't have to worry about it. If that Q is 1, then that means that, OK, my luminosity decreases, but there's just, like, some fixed semi-major axis beyond which planets can't have atmospheres. I can't get in interior to 0.04 AU, say. Unfortunately, we measure Q to be more than 1, which means that this cosmic shoreline threshold actually moves out in semi-major axis space as you go to smaller and smaller stars. And so the slope here of that shoreline sloping outwards is a little bit scary for us who want to study the atmospheres, particularly of planets in the habitable zone here, where if you had an atmosphere, you could imagine liquid water there. But if you don't have an atmosphere, you definitely don't have liquid water at the surface of your planet. And so the fact that for the very smallest stars, you start losing your ability to have an atmosphere, even in your habitable zone, means we might need to rethink where we're making our observations for habitable exoplanet atmospheres. And then the last parameter here feels like a nuisance parameter, this, like, intrinsic width, that is how fuzzy is the shoreline. But I think there's something interesting in here that, like, you can think of this, the fuzziness to be kind of a factor of 50 in flux, where you transition from not having an atmosphere to having an atmosphere. And that fuzziness probably encapsulates a few things. One is, like, intrinsic stochasticity of planets, like Mercury got hit with something or it didn't, so there has to be some randomness there. But it's also probably capturing that our shoreline here isn't, shockingly, a straight line in log linear space. Maybe there's some crinkle to it. There's some extra physics that we should be including. And so the way that we could improve that part of it is to do a better job with each of these terms, right? Like this, how does this incoming energy lift atmospheres off of planets? This is like Dave and Shannon and everybody who's studying how planets lose atmospheres. And then how does this escape driving energy change with stellar type? This is Kevin and Mantis and Sebastian. This is people measuring this directly for stars and putting these together into these kind of ensemble statistical estimate that we could plug into this overall probabilistic model. So to conclude that little bit about the shoreline, the location, slope, and fuzziness are steeper and fuzzier than we thought before. But that's useful, because we now have this model that we can use to make some predictions. And we did avoid estimating XUV radiation for individual stars, although it did show us again that M dwarfs are really nasty little monsters. But with this, we can do some cool predictions. We can ask, like, what's the probability of the first 4 targets that are scheduled for rocky worlds, probability for them to have atmospheres? My money is on LHS 1140b, which is an actual habitable zone planet here. It's not just because I helped find this planet. It really is that it is far enough below the shoreline that we actually have a very strong probability of having an atmosphere. Observations have already been gathered of GJ 3929, and it looks like it doesn't have an atmosphere. So that 24% probability was about right. Like lots of folks are observing the TRAPPIST planets a lot. I don't think most of them have atmospheres. The best bets are TRAPPIST-1F and G, but even those are at about kind of 50% probability according to this model here. So if they find something, that would be super neat, but it's right on the edge. For proposals that we should be submitting, I certainly want to be searching more bigger planets and bigger stars based on like what we've learned from the shoreline here. This gravity really matters and has a big impact. Looking around K-dwarfs, as hard as they are to observe, might be the place where we'll actually be able to see more of these atmospheres. And then also, just to say, there are like some planets that are kind of near the shoreline here, but have gas-rich atmospheres. So like so GJ1214b, another of my favorite planets, like falls right along the shoreline here. But yet this is a like kind of 2.5 Earth radius planet, definitely has some sort of envelope. They're like cool things that it appears to be weirdly very reflective. And so Val and I are working on ways that we might be able to observe this and think about what does this shoreline mean for planets that do have atmospheres in terms of how those have been eroded and how that affects the chemistry of what we're seeing. And then finally, this also tells us that like we need to be studying cooler planets. We can't use this thermal emission trick for everything. And so we actually do have to go do the hard thing that is transmission spectroscopy. And so it means we have to solve this star spot problem that, that stars are complicated and can give you fake transit depth variations. And so we're trying to do this in a few different ways. We have a big program that we've been running on TOI 3884, which is this M dwarf with a star spot on the pole and the planet's in a polar orbit, so it keeps passing over the star spot over and over again. So we can use this to measure the spectrum of a star spot. So Katrina led this really ambitious JWST program, ambitious both in the data we're gathering and in the complexity of figuring out how to analyze these, because there are a lot of tricky things to tie everything together in here. But this gives us a measurement of the contrast of a star spot at every single wavelength. And so we can actually empirically measure the spectrum of the spot, so we don't have to rely on models for making this correction in our exoplanet atmospheres. And then, of course, we also want to be able to do this at all wavelengths. And so Autumn Stevens has been like ramping up our ability to be able to do this from ground-based telescopes. So we have observations of this system both from the Gemini 8-meter telescope, Gemini North, and from Apache Point Observatory, the 3.5-meter, where we're starting to measure contrast spectra for these star spots that will allow us to correct for their effect on exoplanet transmission spectra. And we are even going one step farther in accessible telescopes that Jackson Avery and Autumn and I have been working on trying to commission SBO here on campus for doing wide field slitless spectroscopy of very bright stars, some of which are super interesting and we want to be able to observe, to be able to make measurements of how their spectrum changes as star spots rotate in and out of view from here on campus, where particularly students can be involved in those observations as well. Okay, so that's like a flurry of where things are going. But I want to come back in my last kind of minute here to this plot of the thousands of exoplanets that we know of, and just remind all of us that these planets were found by people, many of you people in this room, and people who put a lot of curiosity and wonder into this and really thought about what would it take to make the dream of there being planets around other stars into an empirical reality by actually making the measurements to see them. And have given us this enormous population to work with, that we can be talking about all these cool things of whether or not rocky planets have atmospheres. And so those, and like, I don't know, people in science right now are having a complicated time. We don't really necessarily know where we're going to be getting our funding for next year. We don't know what our careers look like in the future. I think people are scared. People are worried. But one of the things that I've really valued about being a part of this community here in CU is that there are so many of you who are, whatever is going on in the world, are just this really lovely community of curiosity and wonder that I'm so grateful for, and I hope I get to continue to be a part of it. So thank you for sharing in a community of wonder here. And I'll leave up our learning goals for the class or colloquium today, and leave it there. Thank you. Ooh, wait, Kevin, can we do one thing?
Yes.
Which is, I'm always nervous to ask a question because I don't know if it's like a good question. So could we take like 1 minute and turn and talk to your neighbor about like a thing you got from this talk or a question you had before we come back and ask questions as a group? This is a good time to be like, is that a dumb question? It's probably not. Your friend can tell you. Go for it.
All right, talk amongst yourselves. All right. All right, that brings us to our 2 minutes of talking to your neighbor. So remember how you guys were really quiet when I asked you at the beginning? Now I'm talking like for my football team. Okay. So we like to give the students the first opportunity to ask questions. Questions. Yeah.
Hello. Great talk, Zach. Thanks so much.
Michaela.
For those who don't know me, I'm Michaela Huffman. I work with Dave Brain on how impact bombardment affects planetary atmospheres.
Oh. You're going to ask me about the third plot that I didn't talk about at all.
So I think you may be able to predict my question. But yeah, if impact bombardment tends to add more volatiles to an atmosphere than remove, we'll just assume that, how would that affect some of the parameters that you were talking about here?
Yeah, so in here, so that original cosmic shoreline also did some sort of like approximate scaling of the velocity at which impacts are happening that maybe tells us something about whether or not materials accreting or being lost. But so this question of whether we're accreting, like how does the impact accretion affect this? I think right now that would all be encoded in the fuzziness. And so that could be some additional dimension along here that if we had a good way of estimating this, if we had a model where we could predict how an impact translates into atmosphere gained or lost, and all of the inputs that we needed for that, then that's like a place where maybe we could take away a little bit of this fuzziness and put it into a causal model. But as it is right now, not having those inputs, that just gets absorbed into that kind of factor of 50 of flux. I think what would be really interesting is if we do see some like planets that seem really rocky that are like really appear like outliers relative to the other ones, which we don't see yet, that could be a case for some like very different impact history, maybe.
You're right in the middle.
Thanks. Hi, Zach.
Hi, Maggie.
Is it on? Okay. Awesome talk. I'm really excited about this like incredible like use of Bayesian statistics. I was thinking about like, so you talked about how for like future proposals you'd want to sort of focus more on like bigger planets around like brighter stars because they really more of them line or fall within that like blue region of having an atmosphere. But is there like, do you want to also observe like just more data to like update your priors? So like I noticed an example of this of the number of points really decreases as the luminosity of the star decreases. And that might be an unexplored, you know, like region of parameter space with our data that the parameters you're measuring depend on. So like, do you know about like how we're going to get more observations of that and how it's like maybe complicated by the fact that those stars are more active?
Yeah. So is the goal to like just find an atmosphere, or is the goal to have a better model to understand whether or not planets have atmospheres? And I think they're a little bit aligned because there's this funny thing in this modeling here that if a planet lines exactly along the shoreline, probability is 50% either way. If you observe something that is exactly on the shoreline, it actually doesn't teach you that much about updating the parameters of that shoreline. You need something where there's a very strong prediction for the probability to measure there it does or it doesn't, and then that allows you to update your parameters. So I updated this last night with a couple new planets on there, and it didn't change at all because the planets just like fell exactly along that shoreline, and so it didn't really revise things. And so ideally, I would want a thing where we can make a really strong prediction. And of course, there's this other axis that we're multiplying this by, which is the observability. And so really, you need to have a like, how much time total do I need to be able to revise this? So I'll bug Nestor and Hannah and Kevin and other folks in charge of Rocky Worlds about how we might use this. Hey.
So if the spottedness of a star is a problem for the transmission spectroscopy, shouldn't we be looking at old stars where that is less of a problem?
Yes. Can you tell me which are the old M dwarfs?
Yeah, there are no old M dwarfs.
Yes, yeah. I think that would be, and so like particularly we need to start thinking much more seriously as we like including this in our noise budgets. So like right now we have like when we're writing proposals, we're like, oh, the transit light source effects is going to be terrible. We'll model it. We'll still get down to the photon noise precision. And so I think one of the things I was really proud of in Katrina's proposal for JWST was that she went and simulated, this is what we know about the spottiness of the star. Let's include this as a term in our noise budget in here. Again, both so we could learn about the properties of that spot, but also so that we could have uncertainties on our planetary atmospheres that actually accounted for those spots in there. So yes, if we can parameterize this in a way that we could say, let's spend a little bit more time in terms of photon noise to be able to get to a quieter star, I'd love to do it at this point. It is, yeah.
After some interesting questions from the young folks in the room, just a comment from an older person in the room. Yeah. Namely, it was only a few years ago, maybe as much as 10, where people were developing models for exoplanets ignoring the star. And it's now recognized that the star plays an enormous role in determining whether planets have atmospheres or not. So, excellent talk. I want to give two comments on your shoreline.
Please.
One is it ignores the chemical composition of the planet.
Absolutely.
Namely, a planet with a hydrogen atmosphere will, of course, lose it much faster than a planet with a carbon dioxide atmosphere.
Mm-hmm.
So that's critically important. And second, essentially all stars were more active when they were younger. So there's a whole time sequence here already lost it. Now as the star gets, less active.
Yeah, absolutely. And in here, my conceptual picture here is that our shoreline is mapping a more Earth-like, Venus-like eroded atmosphere where you've lost your hydrogen and helium, thinking of that as a necessary step on the way to losing your atmosphere completely. And so if we can map out that boundary, yes, there's a different hydrogen cosmic shoreline in here. That's a different one that I didn't quite measure here. This is one that's trying to push a little bit more towards secondary atmospheres that are really heavily eroded. To this point about the time effect. In here, though I skimmed over this entirely, I'm only looking at old planets here. So I'm only looking at things that are older than about a half a gig a year, oldish planets. Trying to say all of that integral happened in the past, and it gets folded into the fuzziness parameter of what I have in here. But you're absolutely right that this is, if we want to match this up to a true physical model, these are all factors that we need to incorporate. And I will confess to, I think you and Jack Burns both asked me questions about this during my job interview talk about M-dwarfs being nasty little monsters for their planets. And at the time, I was a little bit more cavalier than I am now. At the time, I was like, well, let's just observe them and see. But now we've started observing them, and we're starting to see. And so, yeah, so that requires a little bit of revision now. So thank you, Jeff.
All right, time for one more question.
Yeah, Sydney.
Hey, Zach, thank you for the talk.
Hey, Sid.
You mentioned how star spots could cause problems and kind of trip you up in measuring the information of the planet. Could stellar flares and brightening spots cause similar problems, maybe in the opposite direction?
Yes.
How?
And it's frustrating in two directions. One is just like a flare appears, and so that's some other signal in your time series that you need to be able to model and correct to be able to get back to the planet itself. The other is this, there's this like bright spot that is an inhomogeneous location on your star that is now also very time variable, even more so than a spot. And so that affects your baseline before and after transit.